Namaste, this is AgriAgent Nepal, a multi-agent AI advisory system for smallholder farmers presented for the AISM 311 seminar at Kathmandu University. I am Baras Manandar with Soba, Bises and Bhavana. The talk has four parts. I said our the problem, Soba places our work against what already exists. Bises takes you inside the system and shows it running. Bhavana present the measurements. Our claims run through all four and it is on the screen now. Agriculture employs about 62% of Nepal's population and contributes close to fifth of GDP. But extension service reach only 15% of farming households. The average holding is 0.8 hectares and three quarters of farms are under the hectare. Here is the observation the whole project rests on. The knowledge is one missing. NARC and the Ministry of Agriculture already publish fertilizers, doses, seed rates, and sowing windows. 85% of households simply never receive them. Productivity here is constrained by distribution, not by agronomy. What is missing is the channel that delivers the figure at the moment the decision is taken. First, arithmetic must be exact. Doses are published per hectare. The farmer stats upload in a biga or kotha. The answer must be sack of urea, DAP, and potash after subtracting the nitrogen the DAP already supplies. Every step is a deterministic and every step a language model performs unreliably. Second, the input is trilingual and code mixed English, Devanagari, Nepali, and Romanized Nepali, often in a single sentence. ALU, and the Devanagari spelling are the same crop, and none of them matches an index entry. Third, silence is sometimes the correct answer. Where no citable figure exists, the system must be declined because a farmer cannot tell a invented number from a source one. Fourth, advice must be outlive the conversation. A number read once is forgotten by the following week. Together, a model asks for a urea dose return something confident and arbitrary. The cost is not a poor user experience, it is a waste season for a household farming. Those properties gave us six objectives. Orchestrate specialist agents, implement calculators as pure function that can decline, fill missing inputs one at a time, diagnose disease with a cascade that can abstain, count every answer, and measure everything.
Digital advisory has passed through three generations. Around 2018, rule-based lookup over a curated knowledge base, then neural retrieval, but still fixed answer templates. From 2024, a language model in front of retrieval. Two recent systems are closest to ours, Agribody from Bangladesh and Argoask AI at AAI 26. Both are genuinely multi-agent, but in every one of them, the number reaching the farmer is written by the generator. This table places us against those systems. Across the features columns, we look like an ordinary member of the family. Photodiagnosis, multi-agent, offline romanized input. The column that matters is the last one. Every other row says the generator produces the number, other says audited calculators. This is an authority comparison, not a feature comparison, and it is where we stand alone. Three further graphs are seen on the screen. Here is the rule behind every decision. The language model reads the question and phrases the answer. It never decides what runs, and it never produces a number. On the left, what it does, on the right, what it is structurally prevented from doing, and the mechanism. It cannot state a number because calculators return pre rendered strings. It cannot name a disease because the cascade label is the diagnosis. It cannot choose a tool because the registry decides. Architecturally, the system is five layers: interface, service, orchestration, agents, and tools, and data and knowledge. A request descends the left or a result ascends the right. No layer reaches past its neighbor, so it can be tested against the stub of the one below. Orchestration itself is a 13 node guarded chain. Each node returns a partial state update merged into a share object, and a node whose intent did not match passes straight through, equivalent to branching, but execution is still deterministic and traceable. Inside it sit a router and five specialist agents. This is whether market, crop, agent, and planner. Each owns exactly one resource, and a shared memory holds the profile, the topic, and the last five runs. The contract between them is the architecture. They exchange structured data, never prose. The vision agent emits a crop, a confidence, a disease, a second confidence, and an abstract flag. Not the sentence, I think this is a lead light. Only the fusion node turns those objects into sentence, and every number in it is a reproducible form, the recorded tool inputs.
Tool selection require a matching intent, a matching keyword, and no veto. Take when should I sow rice seed? It contains the word seed, but it is a dead question, and answering it in a kilogram is exactly what the veto prevent. Underneath our 10 calculator is a pure function over a source data file. When an input is genuinely missing, we do not guess. The system asks for one value at a time, though a form pre-filled with everything is already knows, and a resume call completes the original invocation. If an area can't be parsed, the layer return no value, never zero, because a zero would flow into the arithmetic as a real plot size. Generation is grounded in a trilingual corpus. 65 diseases, entries plus agronomic chunks, 632 document in total, index in all three scripts. The key decision is in the middle of the diagram. The document families are ranked separately and merged under a quota, which tries the obvious alternative, ranking everything in one list. The same dictionary gains, but pull recall fell from 100% to 87. That is the wrong trade because pull recall is what re-ranking worthwhile. Photograph diagnosis is a two-stage cascade. Stage 1 route the crop across 6 classes, including a not leaf a class trained on 53,000 images. Stage 2 is a pre-crop disease model. Note, the two abstain gate because they are different things. This is not a leaf I can read. It is not the same statement as I can't name this disease. Both stages use efficient net backbone and pre-model temperature scaling with threshold fitted on validation logic. The reliability curve tracks the diagonal, so calibration was fitted, not default. And decomposing is diagnostic, it tell you which hub to fix. Let me show the system running. 5 shot and each one demonstrate a claim we have just made. Romanize input with land unit, normalize progressive slot filling a number. From audit, calculator the cascade diagnostic a leaf and refusing an out of scope photograph and advising become an dated task. We just fill the profile of our uh, in our AgriAgent Nepal, and we just select the district and we select a crop we are planting, and we can see the many tools or the agent we have, weather agent, market agent, leaf agent, or crop agent. Let's check the today's weather in Kathmandu, and just our LLM tries to understand the context of the question and try to find out whether to apply calculator or whether to call a weather agent or any agent, and it just read the query properly, and let wait for the result. Okay, now we have got the Kathmandu result, and we can just also take the market price also. We just extract this from Kalimati API key, and we can see the price of today. We can also upload the leaf of any disease, any plant, and try to find other digit, and obviously our again model will try to reason it and try to call which agent. Obviously for now it will call the disease agent, and we have got the result from here. As we already discussed, it called for the two model cascading model, first identify crop and then the disease, and we can see how can we can whenever we ask how to treat any potato disease the plant, obviously try to retrieve the information from the knowledge base, and we get the response in from the knowledge base, uh, and also it also cited the sources. And now we can also ask how many seed we need for maize plant for 1 bigger land. Okay, obviously this is our main feature of this whole system is we are trying to use LLM to call a function. Obviously we have a calculator function, and it try to identify from the key search, it try to identify and find the answer, and we got 15 kg of seed. Okay, let's see the vision cascade model. We can upload any images just from Google search, and let's find, suppose I search the rice disease uh, in Google, and just simple click any photo and download it, and just given to our model, it just detect the rice and also the disease which it have. We can just it to other plant also, potato also, tomato, rice, wheat, and maize. For now we have 5 plants we can test for, and their diseases. Generally our model work on 2 cascade. First is identify the which plant, and second is identify which disease it is.
Here is every subsystem measured separately. We deliberately do not average this. They measure different things on different size sheet, and a single headline number would hide the only comparison that matters. Each stage against the baseline it replaced. Now let us talk about the result. Talking the result in detail, 90.81% into int over 80,000 held out images. The confusion matrix on the right is essentially diagonal. The two weakest models, rice and potato, are exactly the two trained on the small correction. Now, we report end to end because error compounds. A leaf routed to a wrong crop model cannot be diagnosed correctly, whatever that model's own accuracy. Stage 1 recall is 99.3. Stage 2 give correct routing is 99.3. The gap is only the half of the percentage. There are the stage 1 training curves and its confusion matrix. Calibration is per model, temperature is scaled and fitted on validation logic, which is what makes the abstention threshold meaningful rather than arbitrary. Stage 2 decomposition per crop. This is the practical value of a cascade over a single flat classifier. It tells you which half of the system to fix and for which crop. Now, grad CAM over correctly classified the leaves. The attention fall on the lesion, not on the ground or the hand holding the leaf. Now let us talk about the result. On retrieval, the headline is this: indexing the corpus in all three script. Lifted Devanagari hit at all three from 60 to 70%, with English unchanged and pool recall held at 100. The gain required no model at all. The corpus was already in the repository, simply never searched. We also report a negative result. 714 generated question answer pairs are name shaped. They lifted the register that was already strong English and depressed, Romanized and colonial queries, which are registers farmer actually write in, disable and pinned by a regression test. Now let us talk about the result routing and tool planning. The keywords rules scores 100% on the direct queries and 0 on direct. They are not weak, they are narrow. The model fixes exactly that and damages exactly what already worked. So the shift router runs the rules first and console the model only when they match nothing. 78.3% at a median latency of a 0.119 milliseconds. On planning, the deterministic route router reaches 100% exact match with zero false positive. We never net edit the tools against missed one. A missed calculator is a poor answer, and added one is a wrong number carrying the confidence of a right one. Now, three components were built, measured, found inferior, and reported rather than quietly dropped. All three support one conclusion, where is our deterministic component is already precise, replacing it with a learned one straight a guarantee for a probability. We should also be clear about what we cannot claim. Our label sheet were written by us. The referent gate was written after inspecting the router sheet so that the figure is optimistic and there has been no field trial. To conclude, reliability in a low resource getting is obtained by narrowing, not enlarging, the authority given to a large model. In every comparison, the configuration that constrain the model one on routing, on planning, and on retrieval. Now, the future works is an offline capable mobile client and fixed romanized routing which fell sharply under the model and is the registered farmer actually right in. Thank you for watching. This is our AgriAgent Nepal, a multi-agent AI advisory system for smallholder farmers in Nepal. This project wouldn't have been possible without the guidance of our supervisor, Mr. Deepak Babu Amarai sir, whose direction shaped this oak from the beginning. I would like to thank Monosake Sir too for his amazing seminar course. Throughout his session, we learned about the research methodology this project is built on. And finally, I would like to thank my amazing teammates, Mrs. Marasini, Bhavana Ocha, and Baras Manadar, with whom I built this. Thank you, everyone.